From this discussion, we can now define a new concept called impulse. We define it as follows. It's called J. It's a vector, and it's equal to the average force times the amount of time that that force was being applied. And as you can see, as we said earlier, it is a vector, and it points in the same direction as the average force. And so let's use an example to be a little bit more specific about what we mean by average force. So let's do an example of a baseball player hitting a baseball with a bat. And you can see just from this diagram that there's going to be a momentum coming in of the ball. The baseball player is going to swing and hit the bat, applying a force to the ball. That force will change the momentum, change the velocity ultimately, obviously not the mass of the ball, and that will change not only the direction of the ball, but it also probably changes the magnitude. And so if we look though, if we had a force sensor on the bat, we can measure the amount of force that it was applying to the ball, therefore that the ball was applying to the bat, equal and opposite. We would see that there's some kind of low force before it gets hit. As it gets hit, there's a very high force, very steep gradient in how fast that force is being applied, and then it might even kind of wing off the end of the ball or off the end of the bat as the ball is being pushed away, and you can see this kind of weird bumpiness, and all of that is kind of jumbled together. And really, what we want is this average force, which is just the average of all of this data over the amount of time that the bat was in contact with the ball. Obviously, after it's in contact, it's not applying the force anymore. Before it was in contact, it wasn't applying the force. And so this kind of box denotes, where the dashed line is, that denotes the delta t that we're talking about. And where the horizontal line is, where it says F_av, that's the average force where it's been averaged over time. So again, thinking about this, we can now see that for this example of hitting a baseball with a bat, you can see that the average force is quite large for this, but the amount of time it spends doing that is quite short. And in the end, though, the impulse is quite large because the force is very large. And what we're gonna do some examples in class on Wednesday, so that you can get more of an idea about how impulse works. So putting it all together again, we see that we can define impulse as the force average times delta t. And we know that force is change in momentum over change in time. So that implies that the impulse J is the change in momentum. So we give it a new name, but it's really just the change in momentum. And we do need to think about it. So this momentum, obviously, of a particle or a system of particles can change at various times. And so the impulse is really just over a finite time that you are looking at or that you're trying to measure. And we should do a little unit check just to double check that the units for the momentum and the impulse are the same. We can see that the units for momentum are the mass, so kg times velocity, which is meters per second. So you get kilogram meters per second. You can do the same thing for the impulse. We actually get force times time, which is kilogram meter per second squared, because it's equal to ma times seconds. And so you can see the seconds cancel on the top and bottom, and that gives us kilogram meter per second. So it does make sense that impulse is the change in momentum. You basically have the same units, and typically when you have the same units, they're basically the same